Greetings, welcome. So in this video what I'm going to try to do is set up bipolar commutation and then go back to charging batteries off of the spike from your electromagnet. And I want to go to bipolar commutation for a couple reasons. The smaller reason is that you get a little bit better rotation for input power, as far as I can tell. I've never looked at it really formally, but you get a little bit of this push-pull going on, where if you're pushing off of the one magnet and the next magnet is the opposite polarity, and you're pulling off of that at the same time as you're pushing off of that. More important reason is that when you charge batteries with pulse charging, with single diode or half-wave rectification, the batteries sometimes behave oddly after they're charged. So for instance, they don't like to take a conventional charge then. And they just sort of behave differently. That's been reported a lot with lead acid batteries. I'm going to be using nickel metal hydride, but I think it might be the same sort of issue, and I just want to eliminate it as a variable. Just to go a little bit off on a tangent there, is that, you know, if someone were a grad student, they should look into that, because it's implying that the behavior is different depending on whether you're going one direction or the other direction with the voltage, because it does different things with the chemical reaction in the battery. And if that's true, that would be, you know, that would be something really fundamental, that there's a difference there. You wouldn't necessarily be able to say between positive and negative voltage how they behave, but whether the voltage is traveling this way or this way, that what comes off with your spike is different. But in any event, to get around it, what you can do is you can put the voltage into a capacitor, and then when it's there, there's no longer any magnetism, for the most part, any magnetism component. It's just electrostatic, and then you discharge the cap, and you'd call that a cap dump. The other thing you can do is just change the electromagnet so that it's being charged this way the first time, then charged the other way the other time, and use a full wave bridge rectifier. And so now you're getting the full, no longer the half wave, but the full wave rectification, and that's used all the time. So if there was any change in how the battery's behaving, it would only be because of the pulse, because, you know, that's like any kind of wall wart is taking alternating current and changing it into, you know, like 5 volts or 12 volts of DC current. So that's why we're going to have bipolar commutation, north-south, north-south. And now the electromagnet's going to go boom, and then the other way, and you're going to have the whole wave that you're going to rectify with full wave bridge rectifier. In the last video, we were looking a little bit about the effect of mass on a pulse motor, and I haven't forgotten about that, but it's kind of one thing at a time. This took me 3 tries to get this to work, but I'll show you what we got now. Here's a little 2.5 pound weight. You see that nub in there? Just a moment. So you see that just fits in right there. Now this thing is basically locked in. So I mean, you'd want to, if you were spinning real fast, super glue it in, but you don't really need to for just using it now. So this part will get extended up. Put your magnets out here, maybe throw in some space for some pennies out here for old time's sake, and to add a little more mass. And that's the Mark II once it gets done. Now the other reason why I'm just so pleased to have this in place is, to be silly, for homework. Who do you think holds the patent on these grooved weights like this? You might be really surprised. And when I remembered that, I was like, oh yeah, I've got to do this. So if you don't get around to looking it up, I'll tell you when we unveil that machine. But it was like, yeah, I gotta do that. So that's one thing I've been working on. But now we're going to build the bipolar commutation circuit. Unfortunately, I've done it before, and the code is all worked out. So it should just take like an hour to throw together. But I kind of am reminded of Gandalf and the hobbits when they entered Moria. It's a 3-day journey if we don't disturb anything. So hopefully I don't run into a Balrog when I'm doing this. But again, I've done this more than once now. Back in the 70s and 80s, something like this would have taken so long, and you'd have to, there are so many other variables. It's just 4 switches and 2 triggers with these solid state relays. So I think the first thing I'm going to do is I've got, if you can see it, I've got the Hall effect coming into these wires, and I'm running it down there and I'm taping it. And I'm realizing that's kind of stupid. I should just take those and move them out to here and then put the wires in there. And another reason to do that is that at some point I may want to use more than one of the analog digital converter slots there, like the A0 and the A1, and that would be if you want to make, you know, the equivalent of like a V-twin pulse motor. So again, it occurred to me that internal combustion engines are pulse motors, and they're pulse motors with, you know, a fixed length pulse, and so they don't have a lot of torque early on, and you compensate that by giving it gas, which would be like throwing the voltage up, and also changing the gearing. So, you know, if you're running a motorcycle in 4th gear and you turn the gas, it's just going to stall out. And then once they get going, they actually have more torque. So these pulse motors are kind of analogous to that. So when you have like a V-twin, they don't both go at the same time. Or if you have a V8, it's not like all of the cylinders go at the same time. They go boom, 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 all 8. And so that's a way of giving more torque when you're just getting these discrete pulses going, whether it's the explosion in a cylinder or whether it's throwing voltage into an electromagnet. But I'm not working on that this time. First thing is just to get this going, and then do the battery charging. But what we want to do now is get this set up. So I think this arrangement makes more sense. So here's your power, here's your ground, here's your A0. Now let's suppose you wanted a second sensor, and you're not going to use the same timing, so you want a different A0. When they're in there, it's like, well, how do I put the voltage? And so in other words, for the next one, you would just have 2 there, 2 there, and then one goes out to there, and one goes out to there. So here are our 2 trusty Comus AC37 dual channel, so 4 switches. You see the little dot there for the trigger. So we're going to use pins 12 and 13. So where am I? There's 12, there's 13. Now here's your ground coming into here, and then going to there, and then over there, and then to there. And then here are your 2 triggers, and then this trigger also goes out to here. This trigger also goes out to there. It would be nice if those 2 were white, or rather this one and this one were white, but I don't have any tiny ones like that which are white. So now we'll do our little blink all pins, and let's see whether they're working. Okay, so the first 2 switches are working. Now let's try these 2. Okay, so I can see this one only works with my thumbs on it, and then it comes up a bit. So I'm going to see if I can bend the legs a bit or move to a different point on the board, or use a different relay to get it to set well. So I moved it to a little bit different space on the board, and now all the switches work fine. So I just have to remember how to build the thing now. So the important thing with the bipolar commutation is to never have this switch and this switch on at the same time. So never have these 2 switches open and these 2 switches open at the same time, or closed, because then you have a dead short. So to try to remember how to build this, let's just first say pin 13 high, and shut it off for a second, and pin 12 high, and then shut it off for a second. And we're going to try to have the capacitor go 1 voltage and then the opposite voltage. Okay, the first half is working fine. So we got the power going into that switch. And here's the negative switch running out to there. And we see it's charging up, and then it doesn't do anything but just leak slowly out of the cap for the remainder of the time. So now we actually have to do the bipolar part, and after this switch shuts off, charge this the opposite way. So that's where you want to take, so for instance, here's this positive. It has to go to this. So as I was saying, there's that positive. So it goes out to this switch, and then it goes to the negative. And because these two sets of switches are never on at the same time, then you won't have a dead short if I've done everything right. Okay, so now we did that on both ends, and we're getting there. We are getting there. Now it's bipolar, but it's not commutating anything yet. And as I look at it, I think that little part's not doing anything. I think this can go down to there, and that'll go there. Yeah, now we got it. So it looks like something would short, but as long as the switches are all going at the right time, nothing shorts, and it charges up one way and then the other way. So as I said, making progress. So where the cap was is where you put your coil. And since we got thin gauge here and we're at 1.8 volts, it's fine to leave it on for a second. And we see it's getting power. And we know from what we just saw there that it's getting power first one way and then the other way. So a little more progress. Okay, so next we got to revisit our Hall effect, which I have in place now, and I've got the rotor here. You'll notice that dot means north, so that's north facing up, then north facing down, north facing up. They're going north south, north south. So before we even do the bipolar commutation part, let's just see what we're getting. So this is just the monopole commutation that we've been using, and I grayed out all the actual stuff that's doing work, and we're just going to look at the sensor value and look at it 4 times a second, and we're going to spin the rotor by hand. So right now that's what it's showing. We just want to see if it's doing anything. It's not doing much. So for whatever reason, it seems a little less sensitive with this bipolar instead of the monopole. But you see, I set that thing up so you can slide it up and down. So I brought it up a little bit closer to the magnets. And then what we see is something a little more like what I want. I'm bringing it towards a south facing, going down towards about a little under 300. Now north facing, a little over 800. So I'm just doing that. I think that's fine. I think it's ready to spin. Okay, I actually moved the sensor up even a little bit more. So there, we're going down right towards 0, and we're getting up to 1,000 and down towards 0. So now we go to our bipolar commutation program that I put together some months back, and you just need a bunch of different toggle switches for it. Z, T, and I guess that's it. T and Z. So this is set so if less than 100, pin 13 high, greater than 900, pin 12 high. And we can, if it doesn't work, we can take that out to like 150 or 850. And then this is just when it shuts off to be low. So I think we just put it in and it should run. So we'll just run it at 2 volts to start with, and not going to throw in any added mass. I just want to see if the thing's going to spin, and away it goes. Got 2 volts. Spinning pretty darn well. So I'm really pretty sure the bipolar commutation improves them. We're at 2 volts, we're at no milliamps, at under 10 milliamps. So we're under 10 milliamps, 2 volts, and we're spinning at 358. I'm going to turn it up to 4 where we were running before and see what it's drawing milliamp wise, and once it settles in and what kind of rotation we get. So I got the thing spinning now, and it's spinning at 4 volts, and I was thinking, man, this is really spinning well. And so one of the things I did is, if we go back to the last video, this is when we had monopolar commutation and the same setup as here. The rotor didn't have any extra mass from extra pennies in it. There was this thing which has an iron ferrite core to do a little bit of clogging, but nothing was hooked up here as you know, to really provide resistance. So this was the baseline there. We were doing 707.5 RPMs and we were drawing 28.5 milliamps. Now, you know, I only spent maybe like a minute with the monopole moving this around to try to find the exact sweet spot. So, you know, maybe 2 to 5% better or something like that, but it was about in the sweet spot. It was close. So now, and what I did was I changed the duty cycle, the on time, to try to match the RPMs that we saw there, that 707.5, because this would be, you know, like the same, if we were going to do the same thing, this would be the first part of the baseline. So we are doing 714.4.5 RPMs, and we are drawing 17 milliamps as opposed to 28.5. So not quite twice as good, but nearly. And that's because you get the push-pull going on this way. So it's nearly twice as efficient at driving the rotor. So this is probably a good spot to wrap this one up. I haven't actually got to the battery charging part yet, but didn't run into a ball walk when I was putting this together. Everything came together beautifully and easy. So the remaining part is to put in a bridge rectifier and then run it out to, I'm going to run it out to 3 9-volt batteries and run it off of 1 9. I just got to, you know, I don't know, I have no idea, but I'm just starting to think, well, you know, it's a pulse charge. I've seen how mass changes the behavior with the pulse with this. I mean, maybe you can like throw 3 batteries there and it's more momentum. It's sort of a momentum kind of thing like we see here. I have no idea. You know, I got to do the work. And I'm going to be using thicker gauge wire. This is 24. I'm going to be using 22 gauge and hopefully drawing like maybe 50 milliamps on these 200 milliamp, I don't have one in front of me, 9-volt batteries, so that they'll go down pretty quick. We can see how long that 9-volt battery, whether it runs for 4 hours or for 2 hours or for 8 hours, what it does. And with this thicker gauge wire, I'm probably going to be running at like 1500 RPMs. So while I'm doing that battery charging, as long as I'm getting 9 volts out of here, I'm not going to do a dead short or anything, but I'll probably put this through a bridge rectifier and throw it out to another 9-volt battery. So the battery charging will be what I'm going to be working on next once I throw in the bridge rectifier. All right, thanks for coming along, and stay healthy. Keep smiling. Talk to you later. Bye.